No. Okay, so we're shifting to the media industry now. We have two people from Styria. They got funding from Google in 2017, which was the award for the 3 years of hard work in natural language plus processing domain for the news media. This talk is going to be a case study of what they did with 24hours.hr or 24sata, which is like a media company from Croatia. So the floor is yours.
Thank you. Hi everyone. My name is Marko. This is my colleague Enes. He will later proceed. I will just give you the warm introduction into the topic. So our team is formed in early 2015, and now we are almost 20 people together with students on internship. So we grew significantly in the last 2 years. We are working mainly for Styria brands. Styria is a media company, the biggest media company in the region, works primarily in Austrian, Slovenian and Croatian market. Apart from news, Styria also has classifieds or marketplaces in their portfolio. And more on that topic we gave in presentation last year here on the conference. And today we will speak more on the news part. And maybe you can think about why media company would work on heavy R&D in machine learning at all. And actually the answer for that is that users now are consuming more and more media content on non-legacy media systems like Google and Facebook, so social networks. And any way of actually coexisting with these big players for any media companies to invest hardly in technology and machine learning. So what we are doing, like I said, for marketplaces, we are doing mainly computer vision stuff that we presented last year. But for news media, we work more with natural language processing and recommendation systems. And for this, we are now working on personalization project that was, like it was said in the introduction, awarded with a big grant from Google DNI fund last year. So we'll speak a little bit about tags, automatic tagging of the articles. So how we are cleaning the tags, why we should clean these tags at all. Then about contextual recommenders that significantly increase CTRs on the websites. After that, some examples of text generation, and then finally the personalization as we plan to do it. So it's not been already done, we are now working on it. Regarding this Google News initiative, it's actually a way for Google to compensate for the monopoly position on the digital advertising market. So Google is now making this grant where media companies apply and compete to get the projects, and in this way Google is hoping to actually reduce fines from European Commission, I would say. But it's good news for us as a media companies because we cannot otherwise invest so much money into this technology. And within this project, we will actually implement all of the machine learning stuff with our CMS platform, which is called Publicer. And the overall budget of the project is 750,000 euros. And we have 3 main areas in the project. Like I said, the first one is tagging, then recommender system and personalization. We already did some work on the recommender systems, and here we introduced some autoencoder based models that gave uplifts in CTR, and this is now working really good, and this is a hope that we can also make a personalization finally. And for tagging, we actually wanted to solve this issue first, because then we can use then consistent tags to even help the machine learning models that will be produced later, but also there is savings for the journalists when they are inputting texts, but also there are significant search engine optimization benefits for the portals if you have tags nicely placed on your site. And for this to work, we need to make first the cleaning of the tags, because we have 10 years of putting tags manually. So we have bunch of them, a bunch of synonyms, bunch of really similar tags. You can see here, for example, misspellings. You can see here, for example, for the one football team, we have dozens of different tags. There are even some absurd tags, and this is why we have developed this solution for actually cleaning the tags first. And here you can see some nice examples where we were able to merge almost 50,000 tags to almost 8,000 tags. So we made significant improvements in this sense, and the benefits for this is that the tags are more consistent, and after that, when we train automatic machine learning model to predict tags, it has much simpler job to do when it has to predict among 8,000 tags than 50,000 tags. So for those of you, I think mostly who understand Croatian or Serbian language, you can see, for example, here we have a lover, ljubavnica, which is the anchor tag to which we are merging the other ones. And what our system suggests is nezasitna ljubavnica, ljubavnice, sad nešto ljubavnica, ljubavnica I nevjesta, majka ljubavnice. So all different combinations of words and texts related to lover or ljubavnica, so it makes a lot of sense to actually merge all of these texts to the main one. And how this merging is actually done on technical level and all of the other bunch of stuff will my colleague Enes present to you. So thank you.
Hello to all, I'm Enes. I'm going to talk to you about more technical stuff. So how did we do it? So most of the tags, since there are a lot of misspellings, since it's a free entry of tags, it has actually a frequency of 1. So that's really a problem. If you want to create a classifier and you have 130,000 classes and they all have frequency 1, it's not going to work well. So what we can do is have a solid document representation. Each document contains tags, and we can use these representations of documents to assign the vectors to tags. And this is how it's done. You have first TF-IDF, raw text to TF-IDF, then matrix decomposition. You get a document vector, and then you get tag vector by using having a mean of all these vectors containing a given tag. So, for example, in each tag where United States of America appears, each text, you have a document representation of that text, and then you have a mean to get a tag vector. So when the most similar tag in this case to United States of America ends up USA. So you get some semantic similarity. The other part, how we do it, is we take word vectors of tags. So you can pre-train word vectors on Croatian or Serbian, whatever language. Then you can, for example, you would take United States of America, you would take embedding for this word, for this word, for this word, for this word, and you would just take a mean. And this is this gives you a bit different representation. And what fast text also does, it uses subword information, so you can use it for misspellings. Here's an example when you use subword information, and when you use subword information and when you don't use subword information. So, for example, this is a classical example where when you would take only you have a fixed vocabulary, and if you have a misspelling like Zaručnice, and this is the actual example, and you have photographies, then this word is within vocabulary, this one is not. So when you're looking for the most similar tags, then you end up in this column, each tag that contains the word photography, but not something related to weddings. On the other hand, when you use subword information, you have Zaručnice fotografije, fotografije vjenčanja, fotografije s vjenčanja, even zaruke video. So it's related to weddings. The next step in this is, once we clean the tags, we want to recommend the tags. So for two reasons. One is to to make it easier for the journalist. The other one is to avoid this expansion of tags, right? Since we still do not have all the tags cleaned, but we wanted to make the model to get the idea how good it works. So what you can do is just take the most 17,000 most frequent tags, and then you can train a classifier to give this tag. Since text can have more than one tag, it's a multi-label classification. I've already mentioned Facebook's library, FastText, and FastText has a classifier built in, but it uses the softmax layer as an output, which is actually it's mutually exclusive. You have mutually exclusive classes, so it's not really good for multi-label, although it does support multi-labeling in the results. And if we look at the recall at 10, you get 63% recall. What we can do also is to use an article, a model, Doc2Vec, which I'll talk about briefly later, to get the document, the article embedding. Then you can use a shallow neural network, and this gives you 68% recall. To improve it even further, we used time embeddings. So what does this mean? For each tags are dependent on time. For example, if on weekends we have easier content, it's not so much about the politics and so on. In the morning we have more content about the politics. In the evening we have less content about the politics and more easier content. And if you take this into account, then you can also you can discrete the time, and you can model the categorical variables as embeddings. And you can jointly train it to achieve 71%. This is a translated example of our article, and these are the tags. The article talks about the Trump and Melania and some footage about we were very surprised how well it works even on uncleaned tags. So next I'll talk about the contextual recommender, which is we want to have, for any given article, we want to have articles which are similar to given article. This is for two reasons: for reason alone, and for later for the personalization, where we want to have a good representation of what user has read. So similarity, it's not really easy to define because there are, for example, this is the query, Citroën, then you can have the models of the Citroën, or you can have other brands of cars. It depends on the use case which you find more similar. So how would we evaluate our models? Well, the idea is to have humans label some kind of a smaller data set. For example, triplets, where you have an anchor article and two positive article and negative article, where positive article should be closer to the anchor and negative article should be further away from the anchor, by some notion of how humans would define similarity. It's hard. Ideally, we would use this for training, but you need a lot of data. You would need lots of text, which would be human labeled. But we can use some specifics of our data set, and I'm going to show it here. Every article in our data set has the title, the lead, and the text. So what we can use as an anchor is title plus lead, okay? And the text can be used as a positive example. So if this goes through our model, we want, and this goes through our model, we get embeddings for this and embedding for this. And if we take some other article and take the text for embeddings for that text or of that other article, we want that embedding of this and embedding of this is closer to embedding of that other article. now I'm going to tell you something about a few models that we had in mind. Actually, this one we have in production for 2 years already. So you make a classical bag of words. These are your features. Then you input it to autoencoder. Autoencoder is practically an identity function. You want to reconstruct the input, but you go through a layer which has a smaller dimension. So it needs to learn the concepts in order to achieve this. When you're using, for example, SVD, you can do this by SVD, PCA, whatever. You have a fixed representation, and so SVD tries to reconstruct the error, and the vectors needs to be orthogonal. But here you have some freedom how you want your middle layer this embedding to look like. For example, you might want that you have only 15% for each given article, that only 15% of the neurons activate, for example. That can be one. And you can then use these multiple hyperparameters to optimize for some external metric which you can't easily interpret, you can't easily put into a loss function. Another example is this article from 2015-2016, Doc2Vec, and this is implemented in many libraries, where you initialize, for example, if you have 1 million documents, then you initialize, randomly initialize the matrix of dimension 1 million times 300, where 300 is, for example, the dimension that you want to use for representation of your article. You also take some vocabulary and randomly initialize the word embeddings. And then what you do, you select article with that ID and select a random word from this article and a window around this word. And you're trying to use some this embedding and the word embedding, and you try to predict the context. And then you jointly train it. This is another implementation where you try to predict the next word given the paragraph. And when you jointly train this, you get a really good model. But what we want to do is go even further. We want to improve it. If you want to learn a metric, then triplet models are your best bet. But here's how it works. First, the model. You need to have a model. This can be a neural network. It can be whatever you can train. Our neural network is a temporal CNN for text with pre-trained embeddings, for example, fast text embeddings. What does a triplet network do? It has a anchor text, that would be lead plus title. Then we have a positive example, that would be the text from that text. And we have a negative example, and that would be some other article text. Then you run this text through the network, and the output is an embedding of whichever size you want. Here, the output is also embedding, and also embedding here. And then you want to minimize this loss. But you can also, what is the problem with triplet networks? It's very hard to create a good data set. A trivial data set would be, you would, I don't know, take title plus lead plus then text would be a positive example, and random article would be a negative example, because there's a low probability that you'll select a random example which would be closer to the input. But that model would train really trivially, right? So you need hard examples. You need, for example, to train a Doc2Vec model, and then you take first 5 results to query article as a positive example, and from 5th to 15th place as a negative example. That's one thing you can do. You can then take the categories, for example, by taking the anchor from some category. The positive example would be an article from the same category, and negative example would be an article from some other category. There's actually, we used 5 different criteria how define this. And so how is this model then trained? Each type of a triplet, you create a batch from each type of the triplet. Then you push it through the neural network. Then each of these batches has its own loss, and the difference in losses is mostly in this margin factor. What does that mean? We want that articles, for example, if we have easy triplet examples, then we want this margin to be big. You know, you want large distances between the anchor and the negative example, because it's just random. Okay, so you can have different losses. You can even have completely different losses. Like, for example, we can use these embeddings and train it for example, categorize tags from it and so on. So here are some results on our own metric. So we had this triplet type that I've discussed, where you have title plus lead versus text. Doc2Vec actually has the best results, but just a bit smaller is this triplet CNN. But on this category triplet, this is the ability to be within the category, and this is really important since we do have 1 million documents, but we are only recommending from the recent documents. So you have in practice, I don't know, 1,000 or 2,000 documents, and you want that these documents be related to some human notion of hierarchy, and this is the category. And this is especially what is cool, is that even in very low dimensions, these scores are really high when you compare it to Doc2Vec 32-dimensional vector. And why is this important? For example, for once we want to do personalization, these embeddings will go into a model. So if you have, for example, if you want to assess what will the user read next based on user's last 50 read articles, then you would have 50 times 32, and this is 1,500 features, versus if you have a 300-dimensional vector versus 15,000-dimensional feature, which is harder to train. We have millions of users and so on and so on. How can we improve it further? We could add extra tasks. For example, classifying tags would be one. And we can use better pre-trained embeddings, or model which generates better embeddings, like Elmo model. Okay, the next chapter is text generation. The idea, why did we even start with text generation? We wanted to get encoder-decoder model is mostly used in translation. You have you have a sentence in one language, then you run it for some model, for example, convolutional neural network or LSTM, and then you get an embedding. And then you use this embedding as an input to another neural network, for example, RNN, and then the output is a sentence in other language. But what we wanted to do is give a text, and then we wanted to generate the lead text. And we were hoping that this would then be a good representation. If you can generate a good lead text, then you have a good representation. But we stopped doing this because we're using triplet models, but again, we played with it. And we use this Facebook's article where you have some kind of a story prompt. This would be an input to the encoder, and then you generate a story which needs to be connected to this story prompt. So you see here, this is some story about the mage, the warrior, and the warrior here appears. And this is actually what humans wrote, and Facebook then trained a model based on these stories. Here's our example. This is our prompt, and this is what we've generated. So for you who understand the language, it makes some sense. Ok, socijaldemokratski kancelar Sebastian Kurz izjavio u nedjelju da je siguran smjer da postane čelnik Europske unije, te naglasi da neće biti lako u tom slučaju. To će biti prvi put kad su velike promjene posrijedi u Europskom parlamentu, rekao je Kurz nakon sastanka s austrijskim predsjednikom Alexander van der Unk, where Unk is unknown, unknown token. And then this article talks about how he will then become the president of European Union and how Angela Merkel has something to say about it. But this is completely fictional, right? How much time do I have? Sorry. 2 hours. 5 minutes. Okay. Personalization. Okay. Personalization in 5 minutes. So there are two main types of personalization. You have with implicit and explicit feedback. Explicit feedback is actually a lot easier because you have, for each content that user has consumed, user gave some notion how for example, Mark, how much did he like or dislike a movie, an article, and so on. In implicit feedback, it's harder because, okay, if someone has clicked on an article, then you might assume that, okay, user is interested in this article. But if a user hasn't clicked on some article, there's not much that you can assume, especially if a user hasn't even seen the article. So this is an example of explicit feedback. You have some users, you have some items. Items can be articles or movies or whatever. And then they put some marks. And you can, for example, compare them directly where there's an intersection. But for example, for user 5 and 6, they haven't watched the same movie. You can't compare them directly. And how do we solve it? As everything else, we do a matrix decomposition. So then you have a dense representation of movies, dense representations of users, and then you can use these vectors to compare the movies, the users, and some combinations. And here's what you're trying to optimize. This is your ranking. This is a user vector. This is an item vector. And then you try to minimize this error. And this is just a regularization term. You can ignore it. In implicit feedback, the formula looks almost exactly the same. But you can see this parameter here. It represents the confidence about how confident are you that this is actually relevant. For example, if user hasn't seen an article and didn't have any chance to see the article, you can't be confident that that this user didn't like the article and didn't want to read it. So this should be close to 0. And even if this is very wrong, you just penalize your model a little bit. But if you know that someone has seen 5 times, you've seen an article 5 times and you didn't click it, then this confidence should be high and this should be close to 0. So, okay, personalization on 24sata. Actually, when you want to personalize the news portal, it's one of the hardest jobs that you can have because articles new articles constantly come. You want them immediately to be recommendable to all the users. You have a huge amount of users. You do not have any data about the users. You just have their cookie. And the cookie can be from the different devices and so on and so on. So this multiplies the number of users. So how do we want to create this model? We want to create it by having embeddings of last and articles. User has read, time at which user read it, what's the scroll depth, what's the device, location, some engineered features. And here's how, for example, the Spotify does it. So they have a model for collaborative filtering. They have a model for NLP, which have some tags and descriptions and so on. And model which processes audio files, some audio features, and then they combine all 3 features into one. Here's an example how would we do it on 24sata, an equivalent of this. You would have a model for collaborative filtering, a model for custom feature tags, topics, and model for content. For example, doc2vec or this triplet model that we created and so on. And then combine all three, right? But that's not really what we want to do. We want to use just one model, just one big neural network. So if you have all the articles that user has read, if you can instantly, when the new article comes, you can instantly create a vector of it, because you have this model user, a journalist writes an article, goes through our model, you get an embedding, and you have this history. So article 1, article to article n, or let's say that n is 50, you have the reading times, location, day, and so on. And then you have a query. Query is an article that you want to know is it relevant for this user? The output of this model is the probability that the query is relevant. So you go through all the articles that are recommendable, and you know exactly which articles are most relevant to this user. Okay, you can also take it as a sequence. You can use temporal CNN or LSTM. Why is it also good? You can process a lot of data in batches on GPUs. We already have a GPU implementation, so that's not a problem for us. And you can immediately, very fast, if you have 1 million users, you can immediately very fast, once the new article is out, you can calculate for all the users the relevance. Okay. We can use many different. So what was the problem here? Finding a good loss function. That's not really easy. Finding a good architecture and train it. It's not easy to train it, because in many situations you end up with some trivial solutions that you want to avoid. So you want to use negative sampling. For example, you know that user has read some article, and you know that he hasn't or she hasn't read some articles, and then you take these as negative samples, and you punish the model if it predicts that for some article if it predicts that it's relevant, if it's not relevant, and vice versa. And we can use triplet models as well. For example, positive example is an article which was read, and negative which was not. And that's it. Sorry, we had a lot to talk about and very little time, so this was very fast. If you have any questions, you can ask them now and also later. Thank you.
How do you deal with two persons reading from the same device? For example, husband and wife.
We don't. It's not easy to do. Well, okay, it's probably possible to some extent, but this is out of the scope right now.
If I may just add, there is potentially distinguishable in terms that if they are reading it in the different time of day. So you will also take time of the day into account. But also, similar problem is one user on different devices, but then we also rely on separate models for those devices, because we expect that behavior on different devices is also different. So you read different stuff when you are traveling in the tram or a bus to the work, or if you read something at the work or at home in the evening. So.
Yes. Although you can model it by embedding, right? You can say this device or that device, but it's hard, and it's not really confident that we can't be confident about separating this. But if user regularly reads your portal, given any kind of device, it should work okay. So.
2 more minutes for questions.
Yeah. Hello, I have one question. Because you mentioned that for the article, you put you run it for each article. You run it once the article is there. What are the personalization? I mean different scores and all these things. Is it real time when a person comes and you are making the matrix and just the prediction part, or it is once the article is created and then you put the score for this article into the matrix?
Okay.
I know it's a little bit confusing, but did you get it there?
We train a neural network once a night, but this when the new article comes, it has an it's immediately its features are immediately created. This query in the formula, right? And it just goes through the neural network and with all the recommendable articles, and you immediately run for all the users the model, and you have ranking for all the users. It's not in the real time; it's in real time, but it's very fast. And also some breaking news and so on, we don't have control over it. This is what the editorial puts. So it's not that important if article is not recommendable within the first minute.
And are you making this like if the person each day he can read different articles? So do you run this regularly? So if I come the next time, depending on the previous articles?
There is some blacklisting. If you saw some kind of an article 5 times and didn't read it, we blacklist it. If you read an article, we can then again blacklist it.